So we were discussing about the algebraic properties of R. The R is known as a real set of real numbers, and it is associated with two operations, addition and multiplication. So, sum of two real number is real numbers. Product of two real number is again a real number, and okay, and then we have seen the properties attached with the addition and the properties attached with the multiplication and combinedly. So, right, so we have seen the commutativity, associativity for both. Okay, so we have discussed the attached property with respect to multiplication and addition means in R. Okay, and we have discussed existence of additive inverse. So when you talk about inverse of an addition, means additive inverse in specifically you tell. Okay, means if you give the input a plus b, when you will say b is an additive inverse of a, means b has to be minus a, or you can say sum of these two is should be 0. Now, similarly here in the case when you have multiplication, you can, because what you want is with respect to multiplication, if you give the input, you will get the output as the same element. So here is, so 1 dot a, that's 1. 1 into a is equals to a is equals to a into 1. Then we have also seen that existence of multiplicative inverse, which will only exist for non-zero real number. Then we will denote the b, which is such that a dot b is equals to 1 or b dot a is equals to 1. Then we denote this b is equals to 1 by a. So here we have straightforward taken a is it's like 1 by a. Okay. Then we have also mentioned the other properties named as left distributive and right distributive law. So here you are distributing multiplication over addition from the left side, so this left distributive law, and here you are distributing multiplication on the addition from the right side, so that's why it's known as right distributive law. Okay, right. So if all these in total they are 9 axioms. Okay, so I'm just so here is the distributive property. There are 9 axioms. So if you are able to identify sets, okay, with some two operations, okay, and let me specify here. Okay, so if you are able to identify a set S with some two algebraic operations, so they may not be saved as the set of real numbers. So that is why this we are making as with the circles here, means they are different from them. They may be different from there. Then there are and if with respect to addition and multiplication, it satisfies the field axiom, then we say that this is a field. Is a field if S satisfies all field axioms with respect to which we call as addition in S, and which also known by multiplication in S. So this may be this may be not be means you have to identify two operations. Okay, right. So you have the example of, let's say, you may be Z2, that is going to be the set of 0, 1. And if you take any two element in this set is Z2, and if you define, let's say AB belongs to Z2, how will you define A plus B is going to be, you sum, divide by 2, and what will be the remainder? Okay, that you will give you the that will define the addition. And if you and A dot B, how will you define is multiply, and then you divide by 2. Then you have the this will define the multiplication. Am I clear here? So a plus b, how it is defined is a plus b. If you means like remainder, you can say so you divide by 2 means, or is means simple multiplication. Let's say you are taking 1. Okay, 1 comma 1. So a and b are 1. So how it is defined is 1 plus b, 1 plus 1 is going to be, so it originally it is 1 plus 1 is 2, but 2 divided by 2, what is the remainder is 0. Okay, so this will be identified as addition. So you take any two, so 0 plus 0, 0 comma 1, if you take 0 plus 1, that's going to be 0 plus 1 is 1, and if you divide by 2, what will be the remainder? That will be 1. Now look at here. So here 1 is the additive inverse of 1. You can talk about this. So 1 is the additive inverse of 1, because if you're summing 1 with 1, it will give you 0. 0 element. Right? Okay?
Sir, so every time we divide by 2, or because there are 2 elements we are dividing by 2?
It is yeah, it is a notation here. So when see, similarly you can consider the set ZP, which is 0, 1, 2, and so on. Similarly, you can extend this definition. Okay, so these are this, see, real this is the Z2, which we are defining as the set only 0 comma 1 associated with these two operations. And how the operations are defined is, means they are usual, you take usual addition here and then divide by 2 and then take the remainder. Okay, so similarly here. Okay, similarly for the multiplication. So see, whenever you are setting the filled axioms, all the members are coming from the member itself, that set itself. Okay, so here only 0 comma 1 only varying. So now then if you want to talk about 6 comma 7 and so on, you have to go for ZP. So ZP you can take G7, then 0, 1, 2, 3, 4 and so on till 7. Then you add you so what will be here, addition will be defined as a plus b. For this case, what it will be defined is, so here z2, right? So 0 comma 1, so it's ending with p minus 1 here. So p number of elements you are taking. Okay, so you divide by p, so a plus b, you divide by p, and then it will then the remainder, certainly it will be lies between 0 to p minus 1. Similarly, this will give you the a plus b. Similarly, remainder of a into b by p for every element in a and b in z. So that will give you the definition of a of b. So now I left it to you that you verify all the associativity, commutativity, and so on. Okay, so these things are very easy to verify. So a plus b, whether a plus b is equals to b plus a or not. Okay, a plus b plus c, whether is equals to a plus b plus c or not. It's like, so you talk about these filled axioms and verify them. Okay, and that these are very easy to verify. Similarly, you can go with the left distributive, right distributive. So I have given you one different set, like finite set only. This is a finite field. Okay, and earlier we were having a infinite field, because infinite field, why? Because R is a infinite set, and here Z2 is a finite set, ZP is a finite set. You can also get another examples here, set of from natural number also, and so on. Okay, so you need to specify two specific operations, plus and multiplication, such that with respect to them, one you will call as addition, and another will you call as a multiplication. With respect to them, if all the filled axioms are satisfied by the set S or elements of the set S, then you will say that together will be called as a fit. Okay, and here are two examples I have given you, which are finite. So you can't say that, okay, this has to be always infinite. No, okay, it may be a finite set, which also defines a field. Okay, right, fine. Okay, so now a few important observations let's take from the field axioms. So if Z and A are in real numbers and are such that Z plus A is equals to A, then Z equals to 0. So it looks like you just strike these and Z equals to 0. No, not like that. You can do this. You have to prove that Z equals, that has to be 0. How will you show that? That's very simple. That 0 is equals to, I can write A plus minus A, right? Now, I can write this A as Z plus A. I can replace A by Z plus A. Now, you can use the associative property that is equals to Z plus A plus minus A. Now, this is equals to Z plus A plus minus A is 0 and Z plus 0 is Z. It's a single one line answer. Okay, right. What is your doubt in remainder?
Yeah, so how 1 divided by 2, the remainder is 1. So I
So see, 1 by, see, we are, it's very, let me explain here. So if you divide by 1, okay, so what is there? 0, 0, and 2 into 0. So then only this will be the remainder, right?
yeah.
Because, okay, it's simple. Suppose we are dividing 6 or 7 by 2. So 2, 3 is 6, 7 minus 6 is
1.
1.
Again 1.
So further, if you see, if it is still is greater than 2 or greater than or equal to 2, you are still again going to be, right? And so you are going to leave with only when you are having here remainder is less than this divisor. Okay. Okay. So similarly, you can also show that U and B are in R are such that U dot P is equals to B. Means if you multiply by B, it will give you result U is B. Then what should be? It's the U value. U must be 1. With provided B must be non-zero. If B is 0, that space U dot 0 must be 0. Okay, that also need to be proved. Okay, so it's again very simple again. So you have see one is, B is non-zero, so you can have 1 equals to there is a sum A such that this is going to be B dot B. But so we are denoting this A by 1 by B. Okay, so let me write it clear here. So 1 equals to B dot 1 by B. Again, you have to just use the associate. B you can write replaced by U dot B dot 1 by B. That is equals to, you can use the associativity B dot 1 by B. That is equals to U dot B dot 1 by B is 1. And you know by field axioms, U dot 1 is U. Okay, so similarly, you will see the list of observations, more observation in the tutorial sheets as well. Okay, or you may get it from the slides as well, from whenever I will post it. Okay, on your Google Classroom. So try to verify this. These are looks very trivial. Okay, this looks very trivial, but you will enjoy this to prove this. Okay. So yeah, that's also very important. This also very good question. So it has a trick. So you just try to go with it. If A is a real number, then A dot 0 is 0. Okay. It looks like it's obvious. So many times you will stuck with very obvious things. Okay, which is very much obvious, but you will not able to judge how to prove it. Okay, it looks like it's obvious, but it's very, sometimes it is very challenging, very much challenging to prove the obvious things. Okay, so that these observations I can skip, which you are supposed to complete it. Okay, so of course you can refer the book as well. So there are a lot of books available on Google as well. So try to do yourself first. and then you look at the proof. So these are tricky only. Okay, right. Yeah, so subtraction operation in R. So what can you tell about this subtraction operation? If instead of plus, if I use the minus, with respect to minus, I know that A minus B is not equals to B minus A. So associate that commutativity is not there. Okay, so and how will you write this A minus B is defined as A plus minus B. So means now you are free to use this notation as A minus B. That's what it means. Okay, but with respect to this addition, with respect to this subtraction, it is not commutative. Okay, right. So that's we are also observed here. Okay, that's also very important question. But this we will prove it. There does not exist a rational number R such that R square is 2. You know that R square is 2 has the root is square root of 2. And you know the square root of 2 is not a rational number. Okay, so how will we prove that? This is you will not able to find any rational number R such that R square is 2. So now we are going to prove that claim is pair does not exist R belongs to set of rational numbers such that R square equals to 2. So this Q with this here, we will denote it by set of rational numbers. And now, if you look at the set of rational numbers, they are of the form m by n, such that m comma n. Okay, then what is there is m comma n is r belonging to z, and n is non-zero. Right? All the form as m by n form, where m comma n are is any maybe m may be negative, n may be negative, but n must be non-zero. M may or may not be zero. Zero is there. Okay. Now you can also so I can leave one exercise here for you. Okay, so that you must complete it. Okay, exercises show that this Q with addition and multiplication is a field. And example, you can say exercise that show that set of irrational numbers is not a field. Not a field with respect to you have addition and multiplication. Find out why it is not going to be a field. Okay, yeah, right. So now all the members in a set of rational numbers are of the form n by n with n is non-zero. Okay, so now what we do is let's suppose that assume that there exists an R in Q such that R square equals to 2. Then we should certainly arrive with a contradiction. Okay, so and let R is equals to m by n and in a simplified form. Okay, so that there you can say GCD of m comma n is 1. The test common divisor is 1. Okay, that we can make. We can say simplified form. That's fine. That's possible. Okay. Now look at the equation R square equals to 2. This will imply m square equals to 2 times n square. So what does it tell is, and here writing is m must be an even number. right? M must be an even number, means there exists K in a natural number, or you can write K in natural number, such that this is going to be not in K in natural number, or K in Z, K in Z, such that M equals to 2K. Okay, M equals to 2K. So what does this imply? If M equals to 2K, what does this gives you? This implies, now M square equals to 2N square, means 4K square is equals to 2N square. This will implies N square equals to 2K square. So what does this implies now? N also must be even. So where does this contradict is? The greatest common divisor of M and N is 1. Here you have M is also even and N is also even. So the greatest common divisor of M of N is, that's minimum 2, you can say. Right? It's not 1. So it's a contradiction here. So we arrive at the contradiction because we have assumed that there exists R, a rational number such that R square equals to 2. So our assumption is wrong. So it proves that there does not exist R in Q such that R square equals to 2. Okay. Now see, we have already observed the field axioms for the set of real numbers. Now we are in position of defining the notion of positivity. Means when you will, means we want to compare now, right? Whether A is less than B, or B is less than B is A, or A is equals to B, and so on. So how will you define the notion of positivity? Okay, so right, so that we are going to define. Okay, right. So here, a notion of positivity in R. So that's how will we define is, there is a non-empty subset definition. There is a non-empty subset P of R, which we call the set of positive real numbers that satisfies the following properties. So if you take any two members of the set of that set non-empty subset P, then their sum also inside P. So if you take the sum of them, that will also mean sum of two positive real number is positive. Product of two positive real number is positive. So similarly for this second A, B, and P, then A dot P is also in P. Now, what other property is different here? Sum of two positive real number is positive. Sum of product of two positive real number is positive. Then you have the last property here, that is non-dichotomy property, which says that if A belongs to R, then if you take any number from the real set, you can say, then exactly one of the following thing hold. So either A has to be P, or A could be 0, or minus A belongs to P. Okay, so if A is in a negative side, minus A should come in the P positive side, right? If A is 0, A is 0, or if A is positive, A is in positive. So this will identify the notion of positivity in R. So there is a non-empty subset P which satisfies the following property, that will say that that's a set of positive real numbers. Okay, right. So now we have identified the notion of positivity. Now with the help of this definition, now we can actually talk about the comparison, inequalities, you can say. So by looking at this, if you have a non-empty subset, the set of positive real numbers. When I will say A is greater than B, let's take A and B are two real numbers, and I want to say A is greater than B. Okay, then what I can do, so we know that there is a non-subset P of R called the set of positive real numbers that satisfies these three properties. So this we can say if and only if A minus B is greater than 0. If you look, means if and only if A minus B belongs to P. We say that A is greater than B if and only if A minus B belongs to P. This automatically says that A minus B belongs to P, means A minus B is greater than 0, that we are going to use, right? See, whenever A belongs to P, we say that A is greater than 0. If A minus A belongs to P, A is less than 0 or A is 0. So there are only three possibilities, right, by using this. Okay, so with this, what we so from here, what we can note that, okay, so A greater than 0 if and only if A belongs to P. A less than 0 if and only if minus A belongs to P. And A equals to 0. So see, here we are looking at the set of positive real numbers. We are not including 0 here. So we can separately include 0. Then you can talk about greater than equals to 0. Okay, so either A belongs to P or minus A belongs to P, or A equals to 0 number. So it's in between. So dividing, why it is known as trichotomy? Because it is dividing the set of real numbers into three parts, right? One part is the side, another part is the side, and the other part is this 0. Okay, right. So if you multiply by minus here, they all will bring on to this side. So that is why this minus A belongs to. Okay, right. So with this observation here, now we can identify when you will say A is a negative real number or positive real number. Okay, let's say that A greater than 0 means A is a positive real number, that we are going to say whenever A belongs to P. We denote it by A greater than 0. Minus A belongs to P, then we say that A is a negative real number. Okay, and if you include 0, non-negative, non-positive, like this. Okay, right. Okay. So if A belongs to P, then we write A greater than 0 and say that A is a positive real number, that we already explained. If A belongs to P union 0, then we say that it's a non-negative real number. If minus A is in P, then we write A strictly less than 0 and say that A is a negative real number. And so we have the minus A belongs to P union 0, then we write A less than or equals to 0 and say that A is a non-positive. Now you are in the position of comparing two elements in of set of real numbers. So that's a definition now. If let A B belongs to R, if A minus B belongs to P, then we write A greater than B or B less than A. Okay, so these are the definitions. If A minus B belongs to P union 0, then we write equals to sign here. Okay, so now you can have some results for this notion of inequality. So I will go for some of them. So if I go with the first one, A greater than B. Look at there, A greater than B. Whenever A minus B belongs to B. First inequality. Second inequality, when B minus C belongs to P. Now use the first property of P, which says that this implies A minus B plus B minus C also belongs to P, because sum of two elements in P will also inside P. So this will implies B will get cancelled. So A minus C belongs to P. So this will implies A greater than B. Similarly here, this one also you can do. A greater than B means A minus B belongs to B. Now you add and subtract C and you arrange the things, then you will have this still is inside B. If A greater than B and C greater than 0, of course, so again you can use the property here, A minus B belongs to B, and C is greater than 0 means C belongs to P. So their product is also, so AC or CA minus CB belongs to P. That's it. Similarly others. Now similarly for this phi, so if A is non-zero, so either A is less than 0 or A is greater than 0. So you know that if you talk about A greater than 0, let's take A greater than 0, means A is inside P. Right. Now also A is inside P. I use the third property. Second property means A into A. This will implies A into A also belongs to P. Means A square is also belongs to. So this proves that square of a positive real number is positive. What about negative? Less than 0. Whenever A is less than 0, then minus A belongs to P. Then use the same fact that minus A also belongs to P. So you have minus A into minus A belongs to P. But you know that minus A into minus A by from the field axiom, that is going to be A square. Square belongs to P. So what it says is, say whether A is positive or A is negative, square of the is always going to be positive real. Now by following 5, the fifth is very simple because you know that 1 is 1 square and 1 square is greater than 0 by previous. Right? It follows from here. Yeah. For seventh, something like if A is in R, suppose it is it lies inside an interval like close 0 and open epsilon, and you take whatever epsilon greater than 0. If you take epsilon large, it will not help you. If you take epsilon as small as possible, means near to 0, means then you will go, you can say squeeze. The A will be like, so A is also going to be small because A is strictly less than epsilon, but it is greater than equals to 0. So what it tells you is A has to be 0, then only it is possible. Okay, right. So how to prove it? Suppose A is non-zero, you can go with the contradiction. Okay, you can go with the contradiction. Suppose A is a non-zero real number. Okay, then you know, and okay, and let epsilon is equals to A by 2. So you have epsilon which is less than A. You know, right? A by 2 is less than A. Right? And epsilon is greater than, so A is greater than 0. So this is going to be strictly greater than. So you have given an epsilon for which this condition is not satisfied. So your assumption is wrong. What is your assumption is A is non-zero. So A has to be 0. Okay. So these things, I mean, like whenever, so this is going to be used many times now. Okay. So if you have a real number A such that 0 less than equals to A less than epsilon, for every epsilon greater than 0, then A is 0. Okay, right. Now,
Sir, but here if we assume epsilon not greater than A or something like that, why can't we do that?
yeah, you can. Yes, you can. But the thing is, yes, it's like, see, A is an abstract number, right? A is an abstract number, we don't know. What is that number? Fixed, now it's fixed, but it's an abstract number, we don't know what it is. Now, what we want to see, suppose A is non-zero. We are going to say that this possibility is only happen whenever A is zero. Okay, if you look at in the line, so let's say this is 0 and A is somewhere, let's say here, but it is saying that you take whatever epsilon. See, if you take this side here, epsilon, not a problem. But if you take epsilon in between here, suppose A is
Okay, so A equal to 0 for if it says set for any epsilon.
any epsilon,
Therefore,
yes, for
okay,
every,
yeah, yeah.
yes,
Okay,
okay, for every, okay. So,
yeah.
so you will always be able to find a number between 0 to 8 because there are infinitely many numbers sitting inside the interval 0 to 8.
Okay,
Okay, right.
yeah.
So this this is not possible that A is sitting on the right of 0. Because, okay, so it is only possible A has to be equals to 0 for this case space here. Okay, now the next we are going to define the notion of, you can say, length. Okay, length of the interval later on we are going to get it from there. Okay, right. So the absolute value of a real number A, which is denoted by mod A, is defined as follows. So this is very familiar to you. So is going to be this absolute value will result to the value A if A is a positive. It will result you the value 0 if it's a 0 value, and it will result you with minus sign A whenever A is negative, because see, it always needs to be greater than equals to 0, what you want. Whatever the input you give from the negative side or positive side, it will make it positive. Only the sign change if it is required. Okay, and that will have certainly have extension in the function of several variable. We may be check in the means maybe later in the later on semester. Okay, right. So with this absolute value, you have the attached with the same the following properties are attached here. The first property, these properties I hope can be solved by yourself as well. So you can just use the definition of this mod function and then verify these. These are very simple properties which you can prove. Okay, so by following this and this, it will be means from 1 you can observe 2. And the third thing is, if C is greater than equals to 0, then mod A less than equals to C if and only if lies between this interval minus C to C. So these three properties are very simple. If you find any trouble in proving this, so we will look at it in the next session. It's very simple. So only you have to play with the algebra of multiplication. A is positive, B is negative. So you have to take different cases. Okay. For the first case, you have to take whether both is positive. First case, A is greater than 0 and B is less than 0. The two cases need to be taken. The third case is A less than 0, B is also less than 0. But without loss of generality, you can go with these two cases. Okay, because if A is less than 0 and B is less than 0, you can replace A by minus A and B by minus B, and then you can work it out also. Okay, so without loss of generality, you can go with these two cases. Okay, and work it out. Or you can consider all the possible 4 cases that are also possible. A less than 0, B is greater than 0. These are the 4 cases here. And for these cases, you just follow the definition of absolute value. Okay, and then prove it. Okay, similarly for other things. Okay, it's going to be simple. Right. Now, absolute value help you to identify the neighborhood of a point that we are going to learn now. Okay. Now, so that's already mentioned that mod A can be regarded as the distance from A to the origin. Okay, right? So because see on the real line, yes, in the real line, so you have this is 0, whether A is sitting this side or A is sitting this side. So mod A will always give you the length. This will give you the mod A. Distance from A to the origin. Now the distance between A, B and R is going to be given by mod A minus. Right. Yes. So now let's say A belongs to R and epsilon greater than 0. Then the epsilon neighborhood of A is the set, the following set. How it will be reflect in your on the set of real line. Let's say this is A. Now then epsilon neighborhood means you find out, means epsilon neighborhood means you go with epsilon, means epsilon is greater than 0. So you go with A plus epsilon and you have here A minus epsilon. If you open it up and follow the previous property here, that's nothing but it takes all the values inside this interval. Means this is, if you can say this is going to be A minus epsilon to A plus epsilon. It's going to be the open interval here. So open neighborhood. If you include equal to sign here, we will call that as a closed neighborhood. Okay, right. So this will define the definition of epsilon neighborhood of A. So whenever we are not mentioning anything, it is going to be an open. If it is required, need to be mentioned as a closed, we will mention it separately. Okay, so right. So let A is in R and epsilon greater than 0, then the epsilon neighborhood of A is the set given by this. Okay, right. So now with this, we can attach the following problem, that if let A belongs to R and if X is inside epsilon neighborhood of A, if you take any point in X, fix X. Okay, if X you fix in epsilon neighborhood of A, but it is such that it is everywhere in epsilon neighborhood, means it varies with respect to epsilon, then X equals to A. Okay, now so how it will be looks like on the real line is, what it is saying is, here you have the point A. So now you take, so epsilon neighborhood is A plus epsilon to A minus epsilon. Now you take, you are saying that X belongs to epsilon neighborhood for every epsilon greater than 0. So the X will also be lies here inside this, will also be lies here in this. Okay, or means it always cover A. Whenever you're taking neighborhood, means it always covers A. Okay, right, and it may be a very small here and so on. So what it tells you is X has to be only A point. Okay, why it is so? Because you just, if X belongs to V epsilon of, so like mod means mod of let's take another color. What it tells is mod of X minus A is less than epsilon, and which you know is always greater than equals to 0 for every epsilon greater than 0. Just now we have learned the previous property. This is only possible whenever this is equals to 0. This is only possible if and only if mod of X minus A has to be 0. And know that modulus function is 0 whenever the argument is equal to 0, means it has to be X minus A equals to 0, means X equals to A. So we have used the previous result itself to show this. Okay, so X is none other than the A, so it's going to be A only, right? Okay, now we are going to define the supremum and infimum in the set of real numbers. Okay, right. Let's consider a set S, which is non-empty. Okay, which is a non-empty subset, which is very much required. Okay, right. Because empty set does not contain anything, you can't talk about lower bound and upper bound of it. Okay. Then we say that the set S is said to be bounded above. So see, S a non-empty subset of R means what? You have here, let me, means it's going to be lie on this real line. Okay, so it may be like it's going like this. It may be you have the set S, which will be like minus infinity to, so S may be the following things are possible. Maybe finite set also, it may be possible. So minus infinity to A, okay, or you can have B to infinity, or you have both. You may have the open variation as well. So open here, one-sided open. Okay. So all there you can have the A naught to AN, or you may have the non-ending sequence like 1, 1, 2, or we can say 1, comma 2, comma 3, comma and so on, set of natural numbers and so on. Okay. So such type of set is possible here. Okay, right. The set S is said to be bounded above. Means something is sitting on the right of it. You can say. So S is bounded above means it should be means less than equals to, you can say. If there exists a number U such that you take any member from set, it always lies below you. Then each such number U is called an upper bound of S. So this U may or may not unique. Okay, so it will be always infinite. So once it is exist, they are infinitely many. Why? Because S is less than equals to U. Let's say for all S belongs to S. So U plus 1 also follows this. U plus 2 also follows, and so on. So it says less than equals, it's not say equality. Okay, so less than equals to U plus 1, less than, strictly less than also, this will also gives you the upper bound. Now what you can make here is, what is the idea here? So you take the set of all upper bounds, possible upper bounds, U, you can say U, V, W and so on. These all the set of upper bounds. What you can look at is, see, once the upper bound is exists, you know that there are infinitely many. Okay. So other bound, so you can only talk about the least among them. You can't talk about the greatest among them, because afterwards there are infinitely many numbers and it is going towards infinity. Okay. So you can't talk about the, you can talk about the least one. Okay. So in this sequence, let's say U plus 1, U plus 2 and so on. So U is the least one. Okay, so how we will, we are going to define this least upper bound as supremum of the set S. Okay, similarly, I can define the definition for bounded below. When something is sitting the left of the set S. Okay, means you are able to identify a real number U or W, you can say W, such that W is lies below every element of S. So then then you have the another, let's say W minus 1, W minus 2. There are many, infinitely many numbers are sitting on this side as well. So you can only talk about the greatest among them. You cannot talk about the least, because they are decreasing towards minus infinity. But you can talk about the only greatest among them. So greatest lower bound will tells you about the infimum of the set. Okay. So when they exist, may or may not, so a set may or may not have supremum, may or may not have infimum. So then such questions will arise. So we are trying to answer now these questions. So okay, so let me now make it here. The set S is said to be bounded above if it satisfies the following condition, and the set S is said to be bounded below if it is if there exists a number W equals to S for all S in S. Each such number W is called lower bound of S. And again, once it is exists, they are also infinitely many. I am again and again saying it may exist. Suppose you have the interval like minus infinity to 2. It will not exist because minus infinity further what the number is there, we don't know. What is sitting on the left of this interval? No, nothing. We don't know. We can't say. So lower bound itself may or may not exist. Okay, right. Now the set S we can talk about now. Once the set is both, suppose it is also bounded above, it is also bounded below. Means it is sitting in between the real line. It's not okay. It's not going towards minus infinity left hand point, and also right hand point also not going towards infinity. They are finite. You can say the set S set to be bounded if it is both bounded above and bounded below. Means you are able to find, so means W less than equals to S less than equals to U for every S in S. You are able to identify such thing. Then the set S is said to be bound. Okay? Okay, right. So now we are in the position of defining the supremum and infimum of the set. Okay, so that's here. Let S be a non-empty subset of real number. If S is bounded above, so when we will call S bounded above, whenever there exists U in R such that U is greater than equals to S for every S. Yes. Then a number U is said to be a supremum or a least upper bound, what I tried to mention in previous slide, of S if it satisfies the conditions, following conditions. U is an upper bound that is required, that's a minimum requirement. It has to be an upper bound. Okay. The second is if you are able to identify any other upper bound of S, then it must be sitting on the right of it. Okay, means you must be less than equals to. That will assures that that's going to be a least upper bound. Because if you are going to take any other upper bound, that is sitting on the right of it or equals to U less than equals to. Okay, right. So now this not, what is not is saying is there can be only one supremum of a given subset S of R and we denote it by supremum. Means if the supremum exists, it will be unique. Okay, there it may not happen that a set have two supremums or three supremums and so on. If it exists, then it has unique supremum. Similarly for infimum case. Okay, right. So you have the following definition for, you can say infima, sometimes also known as infima. Okay, and suprema. So let's say let's call the definition now. Let S be a non-empty subset. If S is bounded below, then a number W is said to be infimum or greatest lower bound of S if it satisfies the following condition. W is a lower bound of S, right? And if we are able to identify any other lower bound of S, it must be sitting on the left of it.
Sir,
Ah,
is there any compulsion that the bounds must be from natural numbers, or
no,
so if it will be from means the set is not closed, then what will means there will not exist any upper bounds or lower bounds.
no, there are exists. If it is, let me see, closed means, see, if suppose you have the interval like A to B, if both the points are fixed, it's a bounded set. Its a lower bound is A and the upper bound is B.
Okay, even if they are
You
not
need to specify, even if they are not included. So there is a chance that suppose the supremum exists. So this again will give you the feeling that if the supremum is exists or infimum of the set S exists, whether that the supremum or infimum, that number what you got, whether that belongs to the set or not, that also is a no, it cannot be said. Okay, you cannot be say that it's always belong to the set. No, like if you have the set is closed, you take any means a limit point of a closed set, it has to be inside it. Okay, but here in the case here we cannot generalize this, that it's always supremum or infimum of a set may or may not belong to the set also. That also possible. For example, you can take the set S is equals to, this is the one of the set, another set is 1 by n such that n belongs to the epsilon. So this set has, you cannot tell about the yes. So what? So you see what is there is, this is 0 strictly less than 1 by n less than equals to 1 for every n. It's a bounded set. So infimum is going to be 0, supremum is going to be 1. That you can prove. Maybe we can prove it in the later, means a little bit later here. Okay, we will prove it. So, okay. So it may or may not, the set may or may not contain the supremum or infimum. Okay. Similarly, if it, like supremum is unique, infimum is also, if it exists, it's going to be a unique. May or may not belong to the set. Okay. Right. Now this is the equivalent result here for the definition, and that will be useful many time for proving that this is going to be a supremum or infimum. Okay. So what says is an upper bound U. So what is it is starting with the definition that an upper bound U means you have pre-decided that U is an upper bound of S. Okay, is the supremum. So you are going to say that that upper bound, this is because necessary. You must be an upper bound. That's a first condition. Then only you can talk about the supremum. Okay, so an upper bound U of a non-empty set S in R is the supremum of S if and only if for every epsilon. So if for what is this statement, let me read it. If and only for every epsilon greater than 0, you are able to identify an element in S such that U minus epsilon is less than epsilon, S epsilon, that element. Whether this is possible? Yes. Why? See, if epsilon is greater than, let's say, epsilon is greater than 0. And we are saying that U is the, let's say first U is the supremum of the set S. So if you subtract epsilon from U, it's no more the supremum, because if it is the supremum, then U cannot be the supremum because U minus epsilon is less than U. Okay, U minus epsilon is less than U. So U minus epsilon cannot be the supremum of the set. What does that mean? It is not a supremum means it is not an upper bound. This implies U minus epsilon is not an upper bound. Not an upper bound of S. Means what? It is not an upper bound means what? This means you are able to, so this, there is some S for which U minus epsilon is sitting on the left of, and that we are denoting by some suffix here as epsilon. What about the converse here? So conversely now, for every epsilon there exists S epsilon in S such that U minus epsilon is less than S epsilon, which says that U minus epsilon is not an upper bound. Okay, now we have to claim that U is a supremum. So U is an upper bound, certainly. Okay, so U is an upper bound. So first condition is true. U is an upper bound. This is the first condition. Okay, let another, let's take let V be another upper bound, given that U is an upper bound of S. claim is u is less than equals to v. We have to utilize this here. Epsilon is greater than 0. There exists as epsilon in S such that u minus epsilon is less than S epsilon. So let's go with the contradiction. So let u is greater than v. Can I identify let u is greater than v? Can I identify an epsilon greater than 0 such that u is greater than u minus epsilon greater than v? If it is possible, then there will be, so that if so there exists epsilon. I'm saying there exists an epsilon such that u is strictly greater than u minus epsilon greater than v. You want to claim that u is less than equals to v. On the contrary, let's start with this. So we have to contradict with something. So our assumption is wrong. So u cannot be greater than v. So u has to be less than equals to v, and we are done. Okay.
Sir,
So yeah.
sir, but there can be an epsilon naught such that it make the value of u minus epsilon naught less than v.
Yeah, but we are not interested in that. We see there are both possibilities. So there may be epsilon 1 which is lies here, and there may be epsilon 2 which maybe lies here greater than u minus epsilon 2. That's also possible. But we are here. We require this to contradict this. We require at least one. So whether there is exist epsilon, such epsilon or not. That's important. Okay, so this inequality is important for us, not that inequality. So now once this is there, then what you can say now, since u minus epsilon is not an upper bound, so how v can be upper bound? So this contradicts that. This implies v is not an upper bound. Not an upper bound. Even not an upper bound. Okay, so which is going to be our assumption that u is greater than v. Okay, so our assumption is wrong. So here our claim is here u is less than equals to v.
Sir,
Yeah.
concluded that v is not an unknown here.
Because u minus epsilon definitely to be strictly less than some s epsilon because of this condition here. For every epsilon, there exists an s epsilon in such. So for this particular epsilon also, there exists an element of s such that u minus epsilon is less than s. So what it gives you that v is also less than s. So v is less than s means v is not sitting on the completely on the right of s.
So, but here in this, u is not the supremum, so it will be an bound.
Yeah. See what
So
I'm here.
we can also be in upper bound.
Okay, wait a minute. Just let me. So here is the real line. So here may be u. Okay. So you are going to take v. Maybe v. Let's say this is v1. This is v2. Okay. So you are saying u is the least. We have to claim that u is the least upper bound. If v1 is sitting on this side, it's still least. But if v2 is sitting in this side, we have to come with the contradiction. Right? Now, so suppose, see, we know that for every epsilon, there exists an s epsilon in S such that u minus epsilon is less than s epsilon. Okay, this condition is hold true here. Okay, now we will be able to identify an epsilon. Okay, we will be able to identify an epsilon. You can say midpoint of this. You can identify the midpoint of this and you take at that epsilon. So like u greater than v, we have assumed, right? So u minus v is greater than 0. So you can take epsilon is equals to, you have, this is going to be This is going to be u minus v by 2. With this epsilon, there always exists an s epsilon in s such that u minus epsilon is strictly less than s. So what is there is, so this will give you will be able to identify this is going to be some u minus epsilon. You can choose that epsilon, you can say smartly here, and then what will give you is u minus epsilon is less than uh, s epsilon, which is greater than u, which is greater than v, right? Greater than v. So v is now more an upper bound because you have able to identify an s element in s which is sitting on the right of v. So v is no more an upper bound. Okay, so it contradicts to the fact that v is an upper bound. So our assumption is wrong that let u is greater than v. Okay, so hence u has to be less than equals to v. U is a least upper bound, and hence u is the supremum of the set. Okay, right. So we are going to close with the find a property which is known as completeness property of R. Okay, and we are going to take it as an assumption throughout our lectures as well. So every non-empty set of real numbers that have also has a supremum in R. Okay, so if you are having a non-empty set S, subset of real numbers, and such that S has upper bound, says that it has a supremum in R. So supremum of S exists, and is a real number. That's the completeness property of R, or sometimes it is also known as supremum property of real numbers. Okay, so similarly, you can define the infimum property of R also. Every non-empty set of real numbers that has lower bound also has a infimum in R. Okay, identify the infimum property. Similarly, you can go with the supreme property. So with the use of this supreme property to give very important and interesting results, which you are looking like as an obvious things. Okay, which you have sometime you have observed that these are the obvious things. Okay, right, fine. So if you have any doubts, you can ask. To be closing.
Sir, can you explain again what is
Field is a set attached along with two algebraic operations. Okay, so which satisfies the axioms listed above. It satisfies those 4 axioms. With respect to multiplication, it also has satisfied 4 axioms like commutativity, associativity, existence of unit element, existence of multiplicative inverse, existence of additive inverse, existence of zero element, commutativity with respect to addition and multiplication, associativity with respect to addition and multiplication, then distributive property. So if all the properties satisfied by those 2 operations associated with the given set, then that set S together with those 2 operations is known as field.
What was meant by the circles on the plus and minus, plus and multiplication?
Circles, yeah, these are notations used to make it differ from the usual addition and usual multiplication. Nothing more than that.
Okay. So every time we verify that it is a field, that we have to put a circle on that plus.
No. You may have rectangle brackets. You may have triangle also. I don't mind. You need to specify what that operation means. That is important. Okay. Instead of plus, you can make dot. You can exchange those there, but you have to call them. Right? You have to prove that these properties.
Okay, sir.
Okay. The notations are not restricted. Okay.
Okay.
Even you can use less than also, but these are standard things. So try to avoid the things which may confuse others. So that's a very important thing. You're free to use any notation.
Okay, sir. Thank you, sir.
Sir,
Okay.
those were basically user-defined binary operators.
Yes.
Okay.
Yeah.